So this is what this Laplace stuff is for. For most people, is solving differential equations. Now for E, there's just the start of it. It's in there in the notes about the control. For E, mostly it seems to be about you've something called a transfer function, which basically is you've an input and an output, and you actually get in the S domain. Let's just take 1 second on this. I don't really understand this very well, so you can't really ask me too much about it. So how it works is to get, so you've the input signal, output signal, however way you think about that, and then if you go into the S domain, the output signal is equal to the transfer function times the input. This transfer function, yeah, okay. So, can I say anything about this? Kind of. Kind of. Well, more roughly this thing, right? So when you get, so this will be sums of powers of s over sums of powers of s. And if you send it back, basically you can kind of look at this thing, well it's supposed to be just this, but definitely if you look at this thing, you can analyze what's going to happen with the output. If you have things that are of the form s minus a, now what that means is the bottom of this, there's a factor, s minus a, that means there's a root, s equal to a. If you get one of these, a root at a, this is going to be stable. Sorry. So you analyze this thing, basically look at the bottom of this. You solve it equal to 0. You find the roots. If you have a negative root, that would give you a factor like that, that's stable. A positive root would be s minus a, would give you e to the at, which is getting bigger and bigger and bigger, which is unstable. And then there's other ways you can combine them. Now talking about the roots of these is a bit beyond what we're doing, but these guys have imaginary roots. So if you have an imaginary root, then you get oscillations. And then the other one is if you have complex number roots that can go two ways. You can either have this multiplied by a negative exponential, which is stable, or this multiplied by a positive exponential, which is oscillations that are getting bigger and bigger and bigger. That's unstable. So that's basically how you deal with this stuff. Okay. But more kind of physics and typically engineering, it's more often interested in solving differential equations. Now, differential equations for us, the basic one we're going to mostly be thinking of is just a door closer. If there was a door closer on this, so there's a spring force and there's a damping force. And you know where the door starts, you know the initial speed of the door, what's the position of the door for all time. Analyze that. Now, there are other ways of solving that without the Laplace transforms, but Laplace transforms also come into this, and the other thing the Laplace transforms can handle is when you have, say, the door pushed for the first second and stopped, or if the door is kicked. Laplace is the only game in town for analysing things like that that are more discontinuous. So this is the big picture that we have to understand to do the full questions. If a differential equation, so the solution, so for example you have a relationship between the forces on the door and the acceleration, basically Newton's second law is a differential equation, and you want to find the solution, which is the position of the door. So you take the differential equation, it's written in terms of t, we've got one in terms of x, but I'm going to change the t when we do it. You do the Laplace transform, and the Laplace transform, it's going to turn derivatives into simple things. So,
right, if you can handle it because it got kicked, is that because of it got shifted, let's say, the force? Alright?
Yeah,
force shift here.
It's related actually to something called the second shift term.
I was thinking that.
So say if I start pushing it after a second, that's a shift. It's a second late. But the shifting you've seen is in the S domain. But if I push it a second late here, that's in the time domain. So there's another shift term that handles shifts in the time domain. And also the other thing is, so say a kick, for example, is what's called a delta function. And on a bigger set of tables, a delta function just is something here. You can handle it. So that's basically the story. The shifts, it's not quite, the second shift here doesn't quite deal with shifts, it deals with delays. It's probably more accurate. So delays will be better.
If you won't recall steps 2 and 3 there.
Okay. So step 1 is taking class transform, step 2 is doing initial conditions, we'll see that in the question, and 3 is solve, we're going to do it now. 3 is solve for the class transform of the solution. I'll just write it there. Now this is page 105. Solve for, say, Laplace transform. Page 105. Now the differential equations actually for this can solve. Civil engineers use to find the deflection of beams. You can do capacitors. You can do radioactive decay. You can do exponential growth. You can do pendulums. You can do door closer. You can do more than that anyway also. You can do heat transfer. Basically everything in engineering and physics is differential equation. Basically anything, Newton's law or anything like it, you can do. Okay. Now I think what I'm going to do is here, it's kind of explained again. Here's a big kind of story, but we're just going to flake into the examples. Now this one actually, it doesn't quite explain it, but this is actually the equation of a pendulum. Or is it? Kind of. So it's the angle that a pendulum makes with that vertical. It's a little bit off. Theta 0 is a bit big. I won't get into that, but should be theta 0 should be a bit smaller. Okay. So you're over here in the time domain. Okay. And what you're going to do is you're going to transform this equation into an algebraic equation. So you're going to hit that, fix the constant, hit that, equals, and hit that. Okay. Now, this we have to understand f dash to t. It's the same thing as df dt. Yeah? Derivative, same thing. Okay. Now, we're going to hit the first thing here, the d theta dt. Now, what is playing the role of f here? Theta. Theta, very good. And you're going to go, so instead of going from little f to big F, you're going to go from little theta to big theta. Now, there is a big theta, but we'll just draw a big T. Okay? So we're going to use this formula where the role of f is being played by theta. So the first thing when we send it, this derivative, it gets sent to s times, not big F, we're going to use big theta, now we'll just use a big T instead, minus, now this is little f, so this corresponds to, in the time domain, the little theta, fix the constant, 1/10. What does little theta of t get sent to?
Big theta.
Big theta of s, which we're just going to call big T of s. Now I'll scribble it out, but what does 0 get sent to? Constant sent to?
Constant over S.
Constant over S, so it's going to be 0 over S. So you sent this to this to this, and the 0 to this. Now this guy is the initial conditions, this is a separate thing. Now what that is it's the starting configuration of the system. So this is a pendulum, that's saying that now a third, that's about 19 degrees or something like that. So it's about at 19 degrees. Okay, so that's the first step. Now that, there's no derivatives there. It's just an algebra equation. So the next thing is you apply the boundary conditions, or really it should say the initial conditions, that theta 0 is 1/3. So I have S times big T of S minus 1/3 plus 1/10 big T of S. What's 0 over S equal to?
0.
0. That's step 2. Apply the boundary or the initial conditions. Now the next thing is to solve for the Laplace transform, solve for big T of S. Okay. So just so question.
Why did you put the 1/3 in at that stage? Yes, it wasn't in the previously. I know it's above there, yeah.
Yeah, because that, like, we want to solve this for T of S in terms of S. We want it to turn into something like this that we can set back here. So you're going to want to put that in. Now we want to solve this for T of S. What should we get rid of first of all? It's just an algebra equation now.
S.
Constant.
Solving this for T of S. There's one thing that shouldn't be there now on the left that you want to get rid of.
S.
No.
It's your fraction, isn't it?
Yeah, which one?
Minus.
Minus third. Get rid of that. How do you get rid of minus third?
Divided by.
Add to both sides.
Both sides.
Okay.
Why did you get rid of minus third?
Because I want to solve for T of S, so I just want only T of S on the left. Alright? Now this bit is a little, now once you see it, it'd be grand, but it always causes us issues. If for example I had
So you're isolating T of S, and
Yeah.
because it's minus a third, you'll get rid of it.
getting rid of that, yeah. Now if I gave you a question like this, you'd have no problem whatsoever. 5x plus 2x equal to 5. How many x's have you got? 7. We've no problem with that. It's a little bit harder here. If I asked you how many T of S's we have, what would you say?
S and 1/10.
S plus 1/10. That's true. Now, most people can't see it like that. So what we'll say instead is, I'll take out the common factor of T of S, which you can actually do here as well. You can take out the x, and you have 5, left with 5 plus 2, equal to 5, and that's where you get the 7 from. So we're going to take out the common factor T of S here. So I'll have T of S times S plus 1/10 equal to 1/3. Now you might say, well, why the hell are you doing that? Well, I suppose why the hell do you do that? What are we going to do if you're solving this for x? How do you get rid of that 7?
Divide both sides by
Divide both sides by 7. So how are we going to get rid of that?
Divide both sides by S plus 1.
Divide both sides plus s plus 1/10. So we'll end up with 1/3 divided by s plus 1/10. And now I just thought about it, this is not a pendulum. No, it's not a pendulum.
Yeah, so that probably just want to say it.
No, that's not a pendulum at all. It is... I don't know what it is, to be honest with you. I think it's just an abstract problem. Okay, now this is ready to send back. The 1/3 you can fix. And what does 1 over s plus 1/10? Sorry. What does 1 over s plus 1/10 get sent back to? This one rather.
E to the minus 1/10.
Yeah. I might just write this again for you, like maybe like this. 1/3 1 over s plus 1/10. So this is 1 over s plus a goes back to e to the minus a tenth t. So the solution of that differential equation is that function there. If you substitute in t equals 0 into that, you end up with 1/3. If you differentiate this, add it to a tenth of itself, you get 0. And the other ways to solve that, you don't really remember, but well, maybe not. There's separation of variables and integrating factor. Okay. Now, some of you should be a little bit bothered by the thetas and the big T's. Is anyone a bit lost with that? Or you're doing well if you...
Oh, yeah.
That's the hard bit, I think, on this one.
Totally bad for that.
No, honestly.
It's not how we've been doing them all along.
Yeah, but these are the first 3 steps. You've been doing from here to here.
Yeah.
So this is kind of, now we did one of them earlier on. But here we're doing more of them, okay? Now the theta is probably the one that's bothering you, right? So it's set up like this, but it can be lots of different variables. This theta, I don't know, that doesn't really represent anything, but it could be y of t, it could be x of t, it could be theta of t, it could be, could be knocking around, q of t, and all of these things you're going from the time domain to the s domain, and you go from just to signify that you're going from t to s, even though they're kind of the same thing, they're in a different language, just to signify that you're s, you go from little f to big F. Now here we're going to go from little theta to big theta, but we don't really have a big theta, so we just use big theta. Okay, I'm going to go on to the next one. It shouldn't be as troublesome. Okay, in that regard. Okay. So another differential equation. This one doesn't actually model anything in particular. Just an abstract one. So off we go. Now, well, I might write down here the role of f of t. Is played by what?
T to T.
On this question.
3x.
Not 3x.
12.
No. So I'm looking at the dx dt. So what's like the f here? X of t. So whenever you have f's, instead you're going to write x's.
So on the very first line of the last one there, you went to 1/10 of big TS. Why did you go to big TS? There? That's not the way it represents it in the formula.
Because I want to go from little theta to big theta. I didn't have a big theta, so I just used big T of s. I just chose that notation. You can do whatever you want.
Yeah, but why is it?
None of it is actually kind of, there's no maths, we'll say, it's just you're just using one name and giving it a different name.
Yeah.
No, but I mean, it's a big T. Show
Peter,
us in the
Pierre.
formula where
Here's the big
transform to
T.
big T. So you wrote that at the first line, you went S, big T,
Big T, S
minus T to 0.
Little theta 0.
Yeah, plus.
Plus 1/10 little theta of t.
Yeah, so see in what's in print, it's plus 1/10 small t to t. And then when
Small
you,
theta gets sent to big theta of s. Right, no big theta, so I use t instead. Okay. I want to go into this one because it'd be little x, big x, it'd be more straightforward.
Grand.
See, when you were saying there the role of ft is xt,
Yeah.
that mean up top then the role of ft up top was t to t?
Yeah. F. It's played by theta. Now, you're solving this for theta of t. That's the name of the game. And say here you're solving for x of t. How do you know? Well,
So it's always going to be whatever's in front of the t, so
Yeah, like you were dx and you were 3x.
well, the
Both
use the x to
dt,
t. That means you can differentiate x with respect to t. Basically, there's going to be one unknown function in there. X
yeah,
of
but
t.
like if it's dx dt, it's always going to be
X is a
it's
function
always
of
going to
t.
be
X of t.
x and t, or and top and t to t.
T to t,
So
yeah.
like if
Yeah. If it was dy dt, it'd be y dt. Yeah. Okay.
I'm sorry, why is it 0 over S? Where did the S come out in that case?
if you look near the Laplace table, so you send both sides. 0 is a constant, so it should be sent to a constant over S. Yeah.
Right, okay.
Okay, off we go. Now this time it should be a little bit more straightforward because we can go from little x to big X. Okay, so the derivative is the first thing. It gets sent to S. So I'm looking at the just under, I'm looking at this. So I'm trying to send this guy using this to this. It's going to get sent to this, except which instead of F's I have X's. So I'm going to have S times, what am I going to have?
dx, so big X,
Big X, yes, of S minus
small
x of 0. So that's the first one sent. Plus, fixed to 3. What does little x of t get sent to? Big X of S. Equal to, fixed to 12. What does e to the minus t get sent to?
1 over S plus A.
And what's your a?
And my A is T or 1.
I'll just write that over here. So e to the minus t